Let's start our implementation of Conway's Game of Life. Our program, as usual, is divided in three different sections. The first section is the modules, which represents the libraries that we're going to use for this implementation. We need two. The first one is Pygame, which allows us to render stuff using pixels in the screen and, generally speaking, make games. Then we're going to import the random library, which will allow us to randomize the initial states of our tiles. In the data definition section, we encounter the dimensions, which is a tuple, a compound data type with two elements, both integers. The first element represents the total number of columns that our grid is going to have. And the same goes for the second element, but for rows. The cell size represents the dimensions of each of our cells. Because the cells are squares, the width is the same as the height, and those values are going to be both equal to 8. Multiplying 8 by 80 gives us the dimensions of the screen in the width, which is 800. And multiplying the dimensions of the cell by the number of rows gives us 800 as well. So our window is going to be a square of dimensions 800 by 800. FPS represents how fast we're going to run the animation, and we want 10 frames every second, which is rather slow because this is a zero-player game, which means that we are not going to be involved in the updating steps of the game, so we don't really care about the performance that much. It's just that if we let this run for 60 frames or 120 frames per second, or the native resolution at which the machine can render the animation, the game is going to be too fast. We will barely see anything. The next element is going to be the fundamental unit of information in this program, which is the cell. The cell is a class, and this class contains as its constructor the column and the row, which is a positional information that will later have to be translated into coordinates x and y. So here we have cell.c equals c and cell.r equals r. These parameters are passed to the instance of the cell when that cell is created using procedural programming, as we have already seen in Langton's AND. Here we're going to create cell.x as the multiplication of the number of the columns by the dimensions of each of the cells. The same goes for the y-axis. We're going to take the y-axis and make it equal to the number of the row multiplied by the cell size. We need to make a rect. This rect right here will create the square that is going to get filled with pixels. It is the actual boundaries, physical boundaries where this rectangle lives. And these parameters have to be self, because are references to the instance of the class. The state is going to be calculated using the random library. Here the cell.state is going to be equal to 1 if a random number is picked and that number is less than 20. If that number is less than 20, we take 1 and anything else is going to be 0. If you are not familiar with this syntax, this is called a ternary operator. It is a fancy way of making an if-else statement using only one line. This cell is going to have a helper function, which is called the getColor helper function. And its job is very simple. If the state is 1, we return white. The cell is alive, and it receives the color for the cells that are alive. Otherwise, we return black. The next component is going to be a compound data type that represents a two-dimensional array. This is a list of lists, where the innermost list is represented by the creation and appending of every single cell that makes one row. And we generate many rows. That's where the second level of this procedural generation happens. So let's look into line 31 to line 33. For every element x, which we should probably call C, and y we should call r because it represents the column and the row. So for every single column in the range of values that goes from 0 to the total number of columns that we want, we are going to create a new cell that is going to take C as an input In this case, we don't need to multiply it here because we're already multiplying it. And we're also going to pass a parameter called row, which is given by this for loop right here. We're going to get into this one in just a minute. After creating this cell, we're going to append this cell to a cell row. This cell row is going to contain every single column that makes this particular row R. And finally, once we finish populating that entire row, we append the row to the grid. There is multiple ways of doing this, and there is ways in which we can avoid using two-dimensional arrays. But I think that the information naturally lands into this type of... So I'm just going to follow this syntax. Now, the for loop that is here is the one in charge of creating as many rows as possible. Something that we need to generate is also a template. A template for grid. A template is just an outline that suggests how the information inside of an array or a list should be traversed. For every single row in the grid, we do something to that element called row. But the row is also a list, which means that we can also traverse it using a for loop. We say that for every single cell in the row, we can do whatever we want to do. That's these three dots here, but we do it to a component known as the cell. We are ready to proceed. Before we do so, there is just a quick addendum to the variables that we need in the data definitions. These ones are secondary to the scope of this particular program, but it is important for Pygame to work properly. The first one is the generation of the actual screen, which is called the display. This is the actual object that is going to be shown to us in the screen. The clock is going to be a parameter that will allow us to change the speed of the animation. And finally, Pygame init, which normally is used to initialize some predetermined fonts and other assets that the Pygame library has. We are ready to start the coding process. The first thing we're going to do is to create two functions called draw and update, which Pygame relies on in order to work properly. These two functions are going to be run with a while loop and forever. In the draw function, we are going to first draw the background, which is an attribute of the surface of Pygame, of the surface of this Pygame object called display, using the method fill. We're going to make it green. It's because we shouldn't be able to see anything from the background at all. Everything is being covered by the tiles, which leave no spaces in between while not overlapping each other. If we see any green at all, we know that something is going wrong. The next thing we need to do is to render every single tile. And to do that, we're going to trust the template for grid. So I'm going to go to line 37 and copy everything all the way down to line 39. And I'm going to paste it here. I fix the indentations, get rid of the comments. And now I can modify these three dots to do whatever I want to do. In this case, the cell contains information from a method called getColor. That is going to allow me to access the particular color that I should add to the rectangle that I'm about to build. I'm going to take this element out of here for a minute, and then I'm going to call the Pygame sublibrary called draw and the method known as rect. Here I need to pass the following elements. First, the surface on which I want to render the square, which is called display. Then the color. That's where this cell method comes in handy. Then the component that represents the rectangle of this cell, which is simply cell.rect. Remember that this is an attribute that we already generated in the formation of the template for the class cell, which is this one in line 17. That one specifies the top left corner as coordinates x and y, and how far we should go to the right of that point and how down we should go from that point. that should draw a square. Lastly, we are gonna call the Pygame library, the display sublibrary, and the flip method, which is a handshake that allows Python to communicate with the programming language that is actually making these transformations, because Python doesn't have that ability. Let's see what happens if we run this program. I just got an error. It says that there is an invalid color name. Let me check my color names. Oh, it's right here in line 51. So the problem is that this should not start as a hex code. It should just have the name of the color. Let's run it once more and let's see what happens. All right. Now, if I try to move this Pygame window, I can't move it. And the reason why is because in the update function, I need to specify that I want to be able to interact with this window. I'll show you how to do that in just a minute. But just for now, let's contemplate the beauty of the initialization of our system. It looks like one of these old TVs where there was no signal coming in. It just looks like random noise, which is exactly what we are supposed to have. But the important thing is that 20% of the tiles are white. Okay, so let's see how we can make that window move. In the update function, we're gonna run through every single event in the list of events in which the interaction with the window is part of them. For event in pygame.event.get. If the event is of type close, which is called Pygame quit, then we exit Pygame by using the method quit. If I try to run the program once more, this time I'm gonna be able to modify the position of the screen wherever I want it to go. You can see it right here. And now you can see that the resolution of the screen is 800 by 800. We are ready to implement the algorithm. Let's go to the update function. Now, the algorithm starts by first counting neighbors, but we need to do this for every single tile in the system. Remember, we can traverse this using the template for grid. So I'm just gonna copy it from there and I'm gonna paste it in line 62. I'm gonna add an indentation, get rid of the comments, and we're ready to start. Now, the cell contains information that is super important for me, and that is gonna be the number of the row where it is, relative to the grid, and the number of the column where it is, relative to the grid. And I'm gonna save these parameters in variables called R and C that are gonna be recalculated every every time that I move through a different cell. Now, the reason why I call them RRC is to keep things clean. When working with this next step, we need to be as systematic as possible, because making one mistake can have consequences that make the program very hard to debug. So I'm gonna call this neighbors, or NS, and I'm gonna start by creating a two-dimensional list. This list is gonna have 3 elements. The neighbors in the row previous to where this tile is located, which we are gonna access as grid at position R and C. This being the row that precedes the row of interest, which is R-1. So that's gonna be one of the neighbor tiles, the top left corner, the top, middle, and the top right corner. Then we can copy these elements and we can paste them down here. This one is gonna be the position at the current row. So we get rid of the R-1 and we just keep the C. But there is a problem here, and that is that we don't want to count as a state the actual cell that we are looking at this particular state. So I'm just gonna get rid of this and I'm just gonna adjust these spaces right here. The last one, oops, I should not add a comma here. It's already whining about it. So if I paste this down here, this is gonna be at position R+1 in this 3 positions. There we go. So now we have the 8 neighbors in this array. Let's work with the C, which is the number of the columns. Anything that is to the left of this empty space is the column position -1. Everything that is to the right of this center position is going to be the value C plus 1. Before I go any further, please allow me to just check that this information is well formed. I'm going to run it, and okay, now it does complain about not finding that information because we haven't applied the flat torus principle, but it seems that, you know, there is no syntax issues. That means that I am able to just add new lines, use commas here without any, you know, and Python recognizes that as syntax. So that's what I wanted to check. Okay, so we go back to the problem that we encountered during the implementation of Langton's AND. What happens if this tile right here is the one at the right edge of the screen? Well, in that case, there is no neighbors to the right. And if the tile is at the very, very top, at the top edge, there is no neighbors before. To solve that, we use the technique known as the flat torus using the modulo operator. Remember, Python is quite permissive, so using the negative values so automatically, you know, refer to the item that is at the end of the list. But for the added values, we need to give a hint. So let's start first with the columns. Here we're gonna wrap this around brackets, and we're gonna add the modulo. We're gonna say modulo dims at index 0 because that represents the columns. And in r+1, we're gonna do the same thing, but this time we're gonna use modulo dims at index 1. That's it. Let's run it again and let's see if this time it does what's it's supposed to do. And it does really good. So there is no changes still, like there is no updating, but we are getting there. We didn't get any errors, so we're getting there. Okay, so the next thing we need to do is now to apply the rules of the game of life. And it goes like this. So we are gonna create a new variable called total neighbors, and it's gonna start at 0. It is an accumulator. We're gonna create a for loop, and we're gonna say for every single item n in the list of neighbors. Remember that n is just a reference to a cell, which is an instance of a class. It is a class. So we can therefore access the value of its state. We're going to add to the total n the value of this state. If the value is 0, then it doesn't count. We are therefore only counting the number ones. Let's apply the rules of the game of life. If the cell is alive, having the state 1, then we ask if total n is less than 2 or total n is bigger than 3. If the answer is yes, the cell next state is gonna be 0. If the number of neighbors is 2 or 3, then we don't do anything. The tile stays alive until the next generation. Let's add an else statement. If the cell is not alive, therefore is dead. And if, and only if, the total number of neighbors is 3, then we make this cell be alive in the next state. Notice that I'm not changing the state attribute directly. I am changing another local parameter, another parameter called next state. And the reason why is because I don't want the tiles to start moving their states all over the place before I get the chance to calculate every single stage and finish traversing the matrix. Now that I'm done with that, I can copy this part of my template, or I can go to the template for grid again, either way works, and I can paste it down here again. I add the tabulation, get rid of the comments, and this time I can simply update the value of the states. The current state is the cell next state. This for loop happens outside of the previous one. This is its own thing. And it may actually be a good idea to put it inside of its own helper function. I'm gonna do this by simply adding a comment here. Let's call this count neighbors and apply rules. And down here, this one is gonna traverse the matrix a second time, but this time is simply gonna update the states. Let's see what happens. Let's run this and let's see if it runs. We got an error. And my error says that the cell has no attribute next state. The error is right here. The problem is in line 86. It says the cell has no next state. So let's fix that. The problem happened because the class cell didn't have a next state. So I'm gonna call it next state and I'm gonna make it equal to 0. Let's run this again and let's see if it works. And there is Conway's Game of Life. Did you notice that we never use frames per second? We never use frames per second, and that's why the animation is extremely fast. It's very hard to see what is going on. But regardless, you can see the emergence of some very interesting behaviors. It almost looks like, you know, the surface of the pattern by which, you know, water deteriorates walls and the paint starts peeling off. I don't know. That's what it looks like to me. So what we need to do is to apply the frames per second, which is very simple to do. I'm gonna go to the draw function, and after the flip, I'm gonna say clock dot tick at frames per second. Let's run this once more. And this time the program runs much slower. Some very interesting objects are these ones right here that almost seem like they are migrating. They are called gliders. And this is one of the simplest gliders that are there. Now, John Conway was against the use of the name glider for that particular object. He wanted to call them ants. Because he says that they look like ants. Besides that, you have other things like supernovas that sometimes generate big explosions. You saw something over here. And etc. So this is the end of our implementation for the Game of Life. I invite you and actually encourage you to try to make modifications to this system. Something very interesting you can try to do is to keep the states but count the number of iterations that a tile or cell has stayed alive, so that those cells that remained in the game for the longest time start changing colors. And you will see how that new dimension of information is going to provide new insights in the dynamics of this system.